There we go. Getting there. All right. So we hit 50. So let's get going. Okay. All right. So everybody, welcome to the next edition of the ACS Division of Organic Chemistry Virtual Symposium. Really excited for today's speakers. We've got Professor Tianning Diao from New York University and Professor Shannon Stahl from the University of Wisconsin-Madison. Fun fact, we've had pairs of speakers before in different sessions who have worked together before, but we've never had a professor and their PI in the same session. So Tianning was one of Shannon's grad students. So this is really exciting for us to have the pair of them here today. Uh, so hopefully we'll hear some stories, but maybe not. But one of the things we've been doing over the last few weeks has been organizing for the spring ACS meeting that's going to be held in San Diego in March. It's taken up a lot of time for me and Steve and the other program chairs, Emily and Kevin Brown. Um, and One of the exciting parts of the spring meeting is always the awards symposia. And we've been lucky this year in the organic section to have 10 professors and industry folks decide to present their award symposia in the organic division. So we've got a wonderful slate of really varied awards and symposia that we're going to be presenting just the awards for the March meeting in San Diego. So really excited. Congratulations to all of these award winners, and we'll have more news on these folks in upcoming virtual symposium. Right. Sorry for the animations. I didn't put that in on purpose. Steve.
All right. So I think a lot of people are familiar with a very popular program that the Division of Organic Chemistry has been doing for a long time now. That's the Early Career Investigator Awards. And so starting next year, we're trying something different. The ACS is pushing towards collaborative programming. So we have partnered with the divisions of analytical chemistry and medicinal chemistry. So instead of our usual 2 sessions, there will now be 4 spread across all of those divisions. We really hope to have a lot of collaborative or cross-functional awards this time. So the number obviously will double. As before, it will be open to investigators with less than or equal to 10 years of experience in the industrial and government sectors. And nominations will open in the next month at the address at the bottom of the slide. Yeah, so hope to have a really nice pool of nominees. Website has not been updated yet. That's my fault, so don't go to it yet, but soon.
All right. Okay, so one of the in addition to the ACS, normal ACS meetings, every other year we have the NOS, and we're really proud to present this year the 100th anniversary of the NOS. Will be returning to upstate New York in when is it? Oh, it's in June. Yeah, in so the registration for that will start up in a few months, but keep it on your radar. We have a wonderful slate of speakers that are already signed up to talk. It's going to be held at RPI at Rensselaer outside of Albany. So keep it on your calendar, and we hope to see you all there and enjoying the signature event of the Division of Organic Chemistry, the NOS. In addition to all these speakers, we are proud to announce the winner of the Roger Adams Award, who will provide his keynote speech at the NOS, Professor Jacobson from Harvard University. Really proud to have him as part of the program as the Adams recipient. In addition, I found out this morning, got an email from Tetrahedron that he's also been awarded the Tetrahedron Prize for Creativity in Organic Chemistry. And so he will be at the fall meeting of the ACS in next August in Washington, D.C., presenting his award address there as well. So big year for the Jacobson Lab. Congratulations to all. Steve.
All right. So another meeting to keep on your radar, especially if you live in the Mid-Atlantic region, the Northeast, MARM 2025, which is coincidentally celebrating the 100th anniversary of the New Jersey local section of the American Chemical Society. that meeting is being planned right now, and we're accepting proposals in any field of chemistry. So it's like a mini ACS meeting. Expect 1,000 or so people. So we have some really nice keynote speakers, Professor Morgan Meldal, Dr. St. Hilaire, and Dr. Becky Bruck. So yeah, there's a website to get involved, and feel free to reach out to me or anybody on the slide if you are interested in organizing a symposium.
All right. Very cool. Got a lot of good programming going on, including SURF. So SURF is Summer Undergraduate Research Fellowship. Provides an opportunity for undergraduate students to get funded and do summer research with their PIs at their institutions. The fellowship is $6,000 to help support their research, and you get to come and present your work to industry folks at the end of the summer. So we're real excited to continue sponsoring both Steve's company, Merck, and Pfizer are part of the huge number of companies that support this wonderful program. So if you're a undergraduate professor or student, check out the SURF program to see if you can if you want to apply and get some funding for your research and some exposure to a career in pharma. So the applications are due February 19th, and there is a website there at the top of the slide. You can also just go to the Division of Organic Chemistry website for more information. All right, and that's all the announcements we have. As usual, thank you to Hugh and the folks at the Beyond CCHF, Alan Bailey running the Zoom behind the scenes, Jessica and Daisy, as well as Alex Grenning, who they all could not be here today, but Steve and I are really thankful to be working with them. And if you have any comments, questions, or ideas for new speakers, reach out to us, and we'll see what we can do. And without further ado, let's get into the programming. And Steve's going to take it away and present Professor Diao from New York University. And Tianning, why don't you go ahead and get started sharing your slides?
All right, well, so while I'll do the introduction while Tianning shares her slides, and just a reminder, if you do have a question, there's a chat Q&A box, so feel free to post it in. But I'm really excited to introduce our first speaker, Professor Tianning Diao from New York University. Tianning earned her bachelor's in 2007 from Fudan University, then moved to University of Wisconsin-Madison, as Scott had spoiled my intro, earning her PhD from our second speaker, Professor Shannon Stahl, where she published a number of papers on palladium catalyzed oxidation. She then moved to Princeton, developing cobalt catalysts for hydrosilylation, hydroboration in Professor Paul Schierig's lab. In 2014, she began her independent career at NYU, where she was promoted to associate professor in 2020 and full professor last year. Her group broadly focuses on organometallic chemistry to solve problems in synthesis and sustainable energy research, designing catalysts through mechanistic understanding. Her group has developed a lot of really fundamental nickel reactivity with some nice work on difunctionalization, other radical reactivity. And she's also recently published some really interesting papers showcasing novel methods of plastic recycling. So for all her lab's work, she has earned a number of awards, including an Arthur C. Cope Scholar Award, Camille Dreyfus Teacher Scholar Award, and the Organometallics Distinguished Author Award. So today she'll talk about leveraging 1 and 2 electron mechanisms in nickel catalyzed cross-coupling. So take it away, Tianning.
Thank you, Steve, for the very nice introduction. And I want to thank you and Scott and Alan and the other organizers who have given me this opportunity for presenting my research at NYU. And as Steve mentioned, that I worked with Shannon on palladium catalyzed cross-coupling reactions. And nowadays in pharmaceutical synthesis, as well as other organic synthesis in other contexts, palladium catalyzed C bond formation and carbon heteroatom bond formation have been extensively used, and the mechanism of these reactions are now relatively well understood. So many of these reactions go through this 2-electron redox chemistry, starting from oxidative addition to engage the electrophile and the transmetallation to put the nucleophile into the same metal center and then reductamination to make the product. So the concept here is by forming these organometallic intermediates, you can bring down the kinetic barrier of a reaction. But more than that, one can control the selectivity by going through this lower energy barrier reactions. And palladium is a noble transition metal. It's relatively expensive. One may ask, why don't we consider nickel as a alternative for palladium, as it's much cheaper and more earth abundant? And doing a survey in the pharmaceutical process synthesis, one can see that the vast majority of these catalytic reactions are still catalyzed with the palladium, and there is almost no reaction being used, being catalyzed by nickel in process synthesis. So to address this issue, that's how when I started my career, I was asking this fundamental question: what's the difference between nickel and the palladium? So there are obvious advantages of using nickel as a catalyst in terms of the carbon footprint, the cost, and the abundance. But the single factor that has prevented nickel from being used in process synthesis is the high catalyst loading. However, in nature, a lot of these enzymatic cofactors incorporate further transition metals, and this is most likely because of these metals being abundant and they get incorporated through evolution. And this investigation of the mechanism would by previous work has eluded that these first row metals are very good at mediating single electron transfer and radical reactions involving radical intermediates. So that led me to start my career by looking at the fundamental organometallic reactivity between nickel and compare it with nickel and palladium. And through years of study from our lab and others, we've shown that these metallo radicals with nickel, such as nickel 1 and nickel 3 compounds, they are relatively stable. So if you mix a nickel 0 with nickel 2 in many ligand environment, they are going to come proportionate to make nickel 1. And with the palladium and other second and third row metals, their close shell diamagnetic oxidation states and electronic states are more stable. And for that reason, when you use a nickel to activate a electrophile, you can imagine two possible pathways: the classic 2-electron oxidative addition, or the single electron transfer to give out a radical. So in recent years, there are many work in this field have harnessed the innovative activity with this radical activity with nickel. And we've also contributed in understanding the beta hydride elimination barrier. Particularly, we've isolated these nickel and palladium agostic complexes and studied their how different metal affects this beta hydride elimination. And with nickel, this step is a lot slower, and that gives rise to opportunities for using nickel to catalyze cross-coupling reactions with alkyl coupling partners. And finally, the redox potentials between nickel and palladium is very different, with nickel being a lot more reducing, meaning that if you use nickel 0 to activate an electrophile, it could potentially exhibit higher reactivity. And in recent years, it's relatively well accepted now that if you want to use nickel to catalyze the bi-aryl coupling, you'd still want it to behave like a palladium going through a closed shell 2-electron redox chemistry. And with these reactions, it's the strong sigma donor ligands that are most successful in promoting the reaction. But if you want to discover new reactivity with nickel to engage radical coupling partners and create these structures with the saturated motifs, then it's the sigma donor and pi acceptor ligands that are best for stabilizing some of these open shell nickel metalloradical intermediates. So in today's talk, I'm going to first discuss a ligand designing idea that we recently had to promote the 2-electron bi-aryl coupling. And following that, I will introduce our mechanistic work on understanding 1-electron redox chemistry with the nickel. And in pharmaceutical synthesis, Suzuki-Miura coupling has been one of the most practiced reaction for making these multi-aryl small molecule drugs. And by strategically installing heteroatoms and functional groups on these bi-aryl structures, one can optimize the binding affinity and selectivity of these small molecules to their drug targets. And as I mentioned in the beginning, that the catalyst loading for nickel is too high at this point, so people would still prefer to use palladium. And the challenge here is that nickel is not as fast as palladium in catalyzing these Suzuki-Miura coupling reactions. And it could also be easily deactivated by coordination with the heterocycles. So these are the challenges we set out to address. And in the past few decades, there have been many efforts trying to make nickel catalyst faster and more compatible with the heterocycles for Suzuki-Miura coupling. And in this recent mechanistic study by Abidoyo, she has alluded to some very insightful answer as to how we should choose a ligand. So the monodentated ligand that are most of them have been discovered by high throughput screening showed very good reactivity, but they are less compatible with different functional groups, whereas the bidentated ligand could provide better catalyst stability, but they are less reactive. And we, when my postdoc Jing joined my lab, I presented him with this challenge, and I said, why don't you start to understand the mechanism of this diphenylmethylphosphine with nickel? And this ligand has been identified by scientists at AbbVie and Pfizer through high throughput screening for catalyzing Suzuki-Miura coupling for heterocycles. So Jing first, he performed this reaction in high catalyst loading, which allowed him to identify the catalyst resting state being this nickel in a 2 intermediate right after oxidative addition. And then Jing carried out some more organometallic and kinetic studies. What he found out is that the reaction rate is only exhibiting a first order dependence on the catalyst concentration, and it's not dependent on the electrophile nor the nucleophile. And this in combination with organometallic studies, he proposes that this ligand exchange of the nickel halide to nickel hydroxyl is the catalyst, is the turnover limiting step. So this is where the catalyst sits. And as soon as you form this nickel hydroxyl intermediate, the following transmetallation is fast because this hydroxide can coordinate to urbanic acid or ester and direct the transmethylation. So one then might argue that what if I just add more, apply more base or apply a stronger base to promote this step? But it's not that simple because a stronger base could lead to catalyst deactivation by forming these aggregates. So me and Jin thought that we would have to come up with a better idea. How can we improve this reaction with the ligand design? So we came up with this idea of using this scaffold to link a phosphine ligand with a hydroxyl. And we hypothesized that with this ligand, on one end, it could kick off this halide to form a nickel hydroxyl that since this is an intramolecular as opposed to the intermolecular step, you would gain some preference by the entropy, and this step could be potentially faster. And alternatively, one could argue that this pendant hydroxyl could first coordinate to the boronic acid or ester, and this can then direct the transmethylation. And either way, this hydroxyl we expect it to be hemilabile, so it will stabilize the catalyst, but it will not stabilize the catalyst too tightly as a bidentate ligand. So it will still give space for a substrate engagement. And because we don't have a high throughput screening facility, Jin only made 5 ligands to start with, and he immediately found that this ligand, we call it a prophos, with a propane linkage between the phosphine and the hydroxyl. He found that this ligand reacts a lot faster than the monodentate phosphine ligand that was discovered by high throughput screening. And the length of linkage is also important here. As he reduced the length of linkage, the reaction is not as fast. So Jin evaluated the scope of this reaction, and he found that with a simple biaryl coupling, he was able to reduce the catalyst loading, and with the heterocycles, he was also able to observe very good reactivity with lower catalyst loading, such as 1 more%. And this reaction is also compatible with some challenging substrates. For example, 5-member heterocycles are notoriously challenging for palladium, and these other heterocycles like 2-aminopyridine to cyanopyridine are also very challenging. Even with the palladium, one would need a higher catalyst loading, but Jin was able to show a good reactivity with this nickel prophos system. And with this development, now Jin wanted to understand the mechanism of how prophos nickel promotes through Kimura coupling. And with the kinetic studies, he found that this reaction is now first order in nickel and first order in the boronate. And when he independently synthesized this nickel aryl prophos compound right after oxidative addition, and when he mixed it with the boronic acid, he observed a clear coordination of the hydroxyl group to boronic acid, evident by the shift of these protons alpha to the hydroxyl group and it splits into 2 different protons, suggesting some stay coordinated and some uncoordinated. And Jin also established the connection between the boronic acid with the ligand by NOE effect. And with his study, he now proposed that with the prophos, he's shifted the turnover limiting step for the Suzuki coupling to now featuring a pre-equilibrium between the prophos and the boronic acid or ester, and followed by a redetermining transmethylation. And I also want to note that in this system, using a strong base actually deactivates the the catalyst because it could promote this cyclization. And this from genes independent synthesis and resubject the compound to the conditions. This is a inactive catalytic species. So you don't want the chelation to be too tight, but you want the hydroxyl to be there to co-localize the nucleophile to approach nickel. And with this development, Gene recently optimized the synthesis of a ProPhos, and it's now commercially available by 2 vendors. And we are working with our industrial partners to test this catalyst for more interesting pharmaceutical substrates. And with that, I would like to now switch to our work on understanding mechanism of one electron redox chemistry with nickel. And we became very interested in this radical capture step. And it's been extensively proposed in the literature that once you generate a radical, whether it's from photoredox or electroreduction methods or chemical methods, this radical can be trapped at the nickel center, and this forms a nickel-3 intermediate, then undergoes reductive elimination. So this step could potentially, it is to expand the scope of your cross-coupling partners. Basically, anything that forms a radical could be engaged by nickel. And this step could also control the selectivity and the stereo selectivity. And by forming a nickel-3, now you provides a high driving force for the reductive elimination. But prior to our study, there has only been some DFT calculations proposing different kinetic barriers for this trapping step. And there isn't any experimental evidence for this radical interaction with nickel-2. So we thought we would look at this fundamental step in more detail. So we started by applying this nickel dihydropyridine as a catalyst precursor, and this was previously developed by Mercury. And we investigated the interaction of this radical with various nickel compounds. And we immediately found something quite interesting. So with different R groups with aryl, this bond formation is very efficient, giving complete conversion. But when this R group is alkyl, then this reaction does not make a lot of carbon-carbon bond formation product. And when we tried to monitor this radical trapping step by EPR, we first synthesized this nickel aryl, and we found that that over time we observed the buildup of this benzyl radical, but we didn't observe any sign of metalloradical. So this was not observed. But when we switched our nickel complex into this nickel alkyl, then all of a sudden we observed the buildup of a metalloradical signal, which we assigned to this nickel-3 intermediate. So this is suggesting that this R group here controls the radical stability. And we, based on these studies, we propose that with nickel aryl, this radical trapping is the redetermining step. And as soon as you form this nickel-3, the following reductive elimination is fast. So we were not able to observe this nickel-3 intermediate. But with nickel alkyl, once it forms this nickel-3, the following reductive elimination has a higher kinetic barrier, so it gets stuck here, and we could also observe reversible radical ejection, but it does not form the coupling product with this ligand. In recent literature, people like Crystal Seewoff and Dan Wax, they found that with tridentate ligands, it can promote the reductive elimination of alkyl carbon-carbon bond formation, which is very interesting. And then we also characterized, using radical clock experiments, we measured the kinetic barrier for this radical trapping at nickel 2 center with nickel aerial. And we believe this data serves as a benchmark for people who try to develop or design reactions with radical trapping step. Imagine that you have other radical acceptors in the system, then this kinetic data allows to estimate if the radical trapping at the nickel 2 center is kinetically viable. And we've also demonstrated that with a different ligand framework, this radical trapping could be in nature selective. Depending on different ligands, now we can switch the preference for this carbon-carbon bond formation product. And based on this study, we wanted to apply it to methodology and synthesize some challenge molecules. And we became interested in this C-aryl glycoside synthesis. And this project came up during COVID time when a lot of chemists were trying to help by coming up with creative ways to synthesize these antiviral molecules. So by forming a glycosyl carbon-carbon bond, these molecules have better stability towards hydrolysis, and they can exhibit better pharmacokinetics. And another motivation is to make these unnatural base pairs for chemical biology studies of mutagenesis, and also they could be used as strategies for developing new drugs. So our idea is that what if we, since the carbohydrates are quite abundant, what if we find a way to cleave this CO bond and make a glycosyl radical, and then we can use nickel catalysis to cross-couple this glycosyl radical with various coupling partners. And we were inspired by these dihydropyridine precursors that we used in our mechanistic studies. And these precursors essentially can turn an aldehyde into a leaving group to give radicals, because light irradiation could induce this carbon-carbon bond homolysis, and as the formation of this hengypyridine being the driving force. And our innovation is to insert a carbonyl between the hydroxyl alcohol and the dihydropyridine. And by forming these esters, now upon light irradiation or photoredox catalysis, we envision that this cleavage will generate a alkoxy carbonyl radical. This then undergoes a decarboxylation to form a carbon radical. So this step changes the turns from an aldehyde as a leaving group into a hydroxyl as a leaving group. And we discovered these nickel and photoredox conditions were able to take this glycosyl ester, activate it, and upon release of the hengypyridine, it can generate this glycosyl carbonyl radical. This upon decarboxylation forms this glycosyl radical. And we've also shown in our mechanistic studies that this radical trapping at the nickel 2 center could be fast, and it could be selective. So this then could undergo bond formation, and then you regenerate your nickel catalyst that then activates your bromoarine. So we applied these conditions to a variety of furanosides and pyranosides. With these furanosides, the diester selectivity is dependent on the C2 substituents. So the nickel wants to come from the opposite side of this C2 substituent. And we used this method, applied this method for synthesizing a variety of interesting ribose derivatives. And even though this yield is not optimal, but overall, this reaction is still much more efficient compared to previous methods. And this reaction is also compatible with pyranosides. And in these cases, the diester selectivity is dependent on both the C2 substituents and the kinetic anomeric effect. And we've also applied this method to other coupling partners. For example, when we used this carboxylic acid as the coupling partner, we were able to synthesize these C-acyl glycosides, and many of them are quite interesting from molecules that exhibit intriguing biological activity. And for example, when we attach the mannose to glutamic acid, one can envision to use this as a building block for glycopeptide synthesis. And my postdoc Yong Liang, who developed this work, demonstrated that this from mannose one can easily derivatize it into the glycosyl ester, and upon this photoredox coupling with carboxylic acid, he arrived at this intermediate. This then proceeds to make these natural products, and the previous synthesis took many more steps. And this method was also useful for synthesizing these thymidine analogs that have been incorporated into DNA as a way to study the DNA replication and the hydrogen bond, the Watson-Crick base pair, and they actually form very nice Watson-Crick base pair with the counter base. And with that, I also wanted to share our study on the ligand effect for promoting one electron redox chemistry in nicocatalysis. And early on, we've used cross-electrophile coupling reaction as an example to study the overall mechanism with nicocatalysis. And in the previous study, we established that these two Nico-1 intermediates are quite important for controlling the chemoselectivity, as the alkyl electrophile and the aryl electrophile were activated separately by two different mechanisms by these two Nico-1 intermediates. And we wanted to understand how ligands can help tuning the reactivity and stabilize these intermediates. And we did a survey into the ligands that are successful in nicocatalysis cross-coupling, and we found that many of them are good pi acceptors. And that brings up the possibility of ligand redox activity. As you form a Nico-1 intermediate, this unpaired electron could delocalize to the pi star orbital of your ligand to form a Nico-2 with a radical anion on your ligand. And this has important and significant implications in redox potentials of these intermediates. So we started by understanding the redox activity of this pyridine oxazoline ligand. And we first synthesized this Nico-2 compound. And when we reduced it, we found that the electron went to the pi star orbital of the ligand. And this is evident by the EPR signal shows a organic centered radical. And these hyperfine couplings are due to the interaction of the radical to this nitrogen and the hydrogen atoms on the ligand. And then we studied the bis oxazoline ligand, and the reduction of this compound puts the electron on Nico center instead of the ligand. So this is evident by this EPR spectrum showing a Nico center radical. And initially, we thought that this is a strong dependence on the ligand nature, because this oxygen has long electron pair, and they are strong. They can donate into the pi star orbital, so they are strong donors. Whereas these ligands are probably better pi acceptors. However, when we synthesized these compounds with the pyridine oxazoline, now we found that this nickel center is a metal center radical. So it looks like between the same ligand framework, it could be ligand, it could be redox active or non-redox active, and we didn't at that time we didn't understand what factor controls the ligand redox activity. So my student Greg, he did this very detailed organometallic studies. He first reduced this BP nickel aerial, and initially he obtained this ligand center radical, suggesting that the electron went to the BP ligand. But as he waited long enough until the chloride dissociated, he found that now he obtained a metal-centered radical, evident by the structure and the EPR studies. And this effect is also true when he first abstracted the chloride with a salt, and he found that when he reduced this nickel to in just straight ether, he got a metal center radical. But as he add a coordinating solvent THF into this reduction, then he got a ligand center radical. So it looks like the ligand redox activity is not just dependent on the ligand nature, but it's dependent on the coordination geometry. So with that and with literature precedence and Greg's efforts in isolating and studying these nickel-1 metalloradicals, we can now summarize this empirical rule that the square planar 4-coordinate nickel compounds are the ligands are redox active. But with these 3-coordinate trigonoplanar compounds, they often exhibit a metal center radical, so the ligand is not redox active. And when Greg obtained this empirical rule, it actually can be easily explained by a simple d orbital splitting diagram. So whether your electron goes to the ligand or your metal center is dependent on the relative energy of your pi star orbital and your d orbitals. And in a square planar geometry, your empty d square x square minus y square orbital is very high in energy. And in this ligand geometry, the radical prefers to go to the pi star orbital of the ligand. But in the some of the other geometry, your electron prefers to stay in the d orbital of your metals. So once we understood this general rule, then Greg wanted to challenge our previous knowledge whether bioxazolone ligand could ever be redox active. And he found that indeed, once you place it in the right ligand geometry, now the reduction of this square planar compound puts the radical to the very electron-rich bioxazolone ligand. And when Greg moves to an even more electron-rich ligand, and he found that the reduction also puts the radical on this ligand. So it looks like this ligand redox activity is not really dependent on the ligand, but depends on the geometry. And then with many compounds in hand, then Greg, he did a systematic study on the redox potentials of these common intermediates that are proposed in nickel-catalyzed cross-coupling reactions, and he's benchmarked the reduction potential. He found that with a free ligand, these ligands, the reduction potential spans across a broader range, with the pyridine, bioxazolone, pyridine and phenethylene being the easiest to reduce, but this bioxazolone and imidazolone ligands are harder to reduce. But once they form metal organonickel compounds, their redox potential were actually narrowed. And we think this is because once you coordinate the Packard ligands now have a better conjugation. So these ligands, they are harder to reduce, most possibly likely because they don't have very good conjugation between the imine motifs. Now the coordination makes them easier to coordinate. However, one can still tune the redox potential of your metal compounds by changing the four substituents on your pyridine. And now as you change the substituents, they expand through a broader range in their reduction potentials. And to our surprise, this narrow redox potential suggests that perhaps there isn't such a strong ligand effect in terms of their reduction potentials. But what makes these ligands so behave differently in catalysis? So a further investigation by Greg showed that when you perform the reduction on these nickel 2 intermediates, you can see that the CV starts from reversible to quasi-reversible and become irreversible eventually as you go down the series from phenethylene to the more electron-donating ligands. And this is also evidenced, also true with by varying the four substituents on BP. As the more electron-donating ligands destabilizes this redox active intermediate from halide dissociation, and it forms and it prefers to form these 3 coordinate intermediates. And with that, we think we have a way to explain this halide additive effect in cross-electrophile coupling reactions, which have always been shown to be beneficial for these reactions. And we think that they simply provides a way to stabilize these or control the speciation of these reduced molecules. And in an independent study, we found that the following radical formation is dependent on your coordination geometry. So basically, these additives could promote or depromote the radical formation steps. So with that, I'd like to thank my students who've carried out this work. And this is my current group. I want to highlight Jing, who have developed this profile chemistry, which we are quite excited, and we are looking into application of these ligands with our collaborators in the industry. So with that, I would like to thank Steve and other organizers again. And if there's time, I'll be happy to take questions.
Why don't we do one question, and they're typed into the Q&A box, so you can probably answer there's about 3 of them, you can probably answer them offline. So I guess we'll just the first one asked, an anonymous attendee, regarding the Profos story, how do sterically congested electrophiles behave? For example, an aryl bromide containing tert-butyl groups at the ortho position or similar.
Good question. We haven't tried that substrates. We've tried some ortho-substituted substrates, and they work. But we haven't challenged the system with a T-butyl group. But good question. That's exactly one of the challenge.
Interesting. Yeah, really great talk. Okay, so I think just due to time, we can move on to Shannon. And you can answer the other ones in the chat box. And I guess Scott.
All right. Yeah, thanks, Steve. Tianning, that was wonderful talk. Yeah, like Steve said, there's a bunch of questions in the Q&A for you to answer online. And again, folks, ready for Shannon's talk. If you have questions during the talk, please put them into the Q&A at the bottom of the screen. Right. So our next speaker, and I'm really excited to present Professor Shannon Stahl from the University of Wisconsin-Madison. So Shannon received his BS from the University of Illinois and then moved to Caltech for his PhD work with Professor Berka, where he studied the activation of alkanes with platinum complexes. East Coast was next with at MIT with Professor Lippard for his postdoctoral research, where he studied it's big shift in his studies to enzymatic work on methane methoxygenase. And in 1999, he began his career at Wisconsin, and he's been publishing an amazing amount of really cool work since, and most recently on a lot of oxidative and electrochemical reactions. He's an active industry collaborator and a member of the National Academy of Sciences and the American Academy of Arts and Sciences. And in addition to his long list of awards, he was awarded the ACS Award in Affordable Green Chemistry a few years ago. So it is my pleasure to introduce Professor Stahl, and take it away, Shannon.
All right. Thank you, Scott and Steve and team. And it's a real pleasure to be able to share the podium with Tianning, a former coworker. So I'm going to stay on some similar themes, and especially seeing some electrochemistry, which will be the focus of my presentation today. Kind of jumping between oxidation chemistry as well as reduction chemistry, where we'll see a little bit more nickel catalysis. I thought I would just start by kind of explaining a little bit about how I ended up in electrochemistry. So as some on the call may know, we started here at Wisconsin about 25 years ago, focused on aerobic oxidation catalysis. Of course, this is where Tianning cut her teeth, so to speak, and did a lot of beautiful palladium catalyzed work, some methodology, some scale-up work with Lilly, but also some beautiful mechanistic work, and you can see that that's continuing to this day. So that was some aerobic oxidation catalysis. And then about 8-9 years into my career, we had a chance to get involved in this topic of solar fuels production. It was just at the time there was an energy crisis, a lot of money going into electrochemistry. It wasn't in the organic chemistry space. In fact, this is actually where we started learning about heterogeneous catalysis. So this was a study. James Gherkin joined my team at the time as a postdoc. He's now continues with me as a leader in many of our efforts related to electrochemistry. This is really where we started getting familiar with electrochemistry. Shortly thereafter, a few years later, we started focusing on oxygen reduction, which is actually the key reaction that's also present in our aerobic oxidation catalysis, but this was more related to fuel cells. We even built a little fuel cell using molecular mediators. So this was, again, kind of an extension of our understanding and experience in electrochemistry. And then I had the pleasure of working with Mohammed Rafi, who came from Iran as a visiting professor at the time, and has since decided to stay in the U.S., much to our benefit here in the U.S., at the University of Missouri, Kansas City, doing organic electrosynthesis. And so that's really where we kind of made the transition, an extension, if you will, from the energy space into the organic electrosynthesis space. But I think it's worth noting, way back at the beginning, all we were doing in our aerobic oxidation reactions was coupling two redox half reactions. So it really conceptually is not a leap. I think anyone who's done electrochemistry or is new to electrochemistry realize that there are some technical challenges and dealing with new equipment and new apparatus that can present a barrier. But conceptually, from a chemicals perspective, it's really the coupling of a reductive half reaction where we're reducing oxygen and then oxidizing an organic molecule that we continue to do in the context of our electrochemistry. Maybe a shameless plug. Mohammed actually is one of the individuals who kind of coaxed me into joining him in a organic electrochemistry short course that we've put together. If you're interested in learning about the principles and basics of organic electrochemistry, one of my passions is kind of bridging the worlds of kind of basic electrochemistry or organic chemistry, excuse me, into the world of electrochemistry, because I think this interface presents a barrier, and that's part of what we cover in the course. Rather than memorizing this, it's just on our website. There's a link that's available. Okay, to the topic at hand, essentially what I wanted to discuss is this term that you sometimes see in the literature called reagent-free electrochemistry, which I thought I would discuss because it's kind of a direction that is of interest to us. I think this term reagent-free can be misapplied. And so let's talk about kind of when it's appropriate, when it's not, briefly. And I also think it's interesting if there's some pharma people on the call, for example, especially in the process space, oxidation reactions are one of the classes of reactions that we tend to avoid. because they often use toxic, hazardous reagents that can be challenging to work with. And so we tend to prefer kind of non-redox cross-coupling, for example, or reduction, hydrogenation, or reactions. In electrochemistry, it actually turns out that oxidations are somewhat privileged because oxidations, of course, formally, as I'll show you in a moment, in fact, maybe I'll just go there. Essentially, any oxidation reaction can be written as an electrochemical half reaction that involves dehydrogenation. I show that even in the context of an epoxidation. Usually, kind of when we take sophomore organic chemistry, we talk about oxidation reactions. There's usually a reagent that is kind of adding like an oxygen atom to the molecule. So we don't usually think in terms of redox half reactions. But essentially, an epoxidation can be written as just an oxidative coupling of water and an alkene, for example. And so this is essentially any oxidation reaction could be written in such manner. There's other flavors of oxidations maybe that involve boron instead of protons. But the idea is that these oxidative coupling reactions where you release 2 electrons and then 2 protons, or a proton and another electrophile, is a way of thinking about oxidation reactions differently. In fact, we've spent a fair bit of time kind of going to the NIST, National Institute of Standards and Technologies website to get free energies that we could translate and start thinking about reactions from a standard potential perspective rather than a free energy perspective. I think we kind of grow up in organic chemistry mostly thinking about free energy. So that's why oxidations in some respects are privileged, because you're just pulling electrons and protons off of a molecule, whether it's an oxidative coupling, whether it's a dehydrogenation of the organic molecule, like an alcohol oxidation, for example. And what that means is that those protons and electrons can be recombined here on the other side of the electrode, at the other electrode, to generate hydrogen. And so these, I think, can be legitimately called reagent-free. If you're going to do an electrochemical reduction, reagent-free is kind of is not viable, because essentially now we're going to be taking a substrate and we have to have a way of adding electrons to the molecule. If we're going to add electrons, that means we need a reagent or a source of electrons. It can come in the form of a sacrificial electrode, of course, and that means that we're just going to be spitting out metal ions into solution. So our electrons come from there. Or we're going to be using a chemical reductant that has to be consumed as an electron donor. So there's no way, you have to get electrons from somewhere. So reductions will not be reagent-free. And so then the question is how can we drive the most sustainable electrochemical reductions possible? And that will be part of the focus of today's talk. I've already talked about this, so I'll skip through it. The story today kind of begins with this aerobic oxidation theme that comes back to the early days of work in my lab, where we were interested in all manner of oxidation reactions. We especially focused on these redox half reactions that we could stitch together. But my postdoc was obviously focused on methane monooxygenase, was focused on a different class of aerobic oxidation reactions. I show that here, partly because it illustrates some important principles. So methane to methanol uses O2, but it also uses a reductant. And so there's this kind of reductive activation of O2 that's involved. And this has kind of been a longstanding complication in the synthetic oxidation arena, because if you want to use O2 as an oxidant, which was kind of one of the kind of goals that I set forth when I started my career at Wisconsin, we don't want to add a reductant just so that we can use molecular oxygen. And so what we'd really like is a dioxygenase that actually could deliver both oxygen atoms to the organic molecule to make 2 equivalents of methanol. There are enzymes that are called dioxygenases in nature. Many of them are, I think, misnomers. I mean, they formally transfer oxygen to 2 organic molecules, but often one of them is a sacrificial substrate like alpha-ketoglutarate. And so, it's really no different than adding NADH, a hydride source, to make water. You could argue that this is a dioxygenase if you use that nomenclature, because we're oxygenating protons, and so I think nobody would call that a dioxygenase. And that's why I really don't like this term dioxygenase when there's a sacrificial substrate that's not kind of the chemistry of interest. But nonetheless, the question is what would it take, or what's the origin of this intrinsic barrier, or why do we need reductive activation of O2? This is essentially coming back to the thermodynamic principles. So oxygen, of course, if you follow any of the energy literature, that number of 1.23 volts will be embedded in your head. And so the idea of reducing oxygen to water with 4 protons and 4 electrons has a thermodynamic potential of 1.23 volts. Hydrogen, of course, is our standard. That's where we set our 0 value. And then the other two values that are noteworthy is the 2-electron reduction of O2 to hydrogen peroxide. Turns out that has a potential of about 700 millivolts. And then over here, it turns out that you can reduce oxygen to hydrogen peroxide to make a stronger oxidant. And so this really underlies, I think, what nature is doing is it's not just trying to balance redox. Methane to methanol is a 2-electron oxidation. O2 is a 4-electron oxidant. It's not just balancing redox by throwing in a reductant. It's actually doing itself a service by making a stronger oxidant to go after a challenging CH bond that has kinetic barriers to overcome. And so that's really the essence of a monooxygenase. That's where the term reductive activation of oxygen comes in, is that you reduce oxygen to hydrogen peroxide, make a stronger oxidant. By the way, this is kind of one of the points that we raise in this little tutorial synopsis that we put into JOC, kind of talking about the language barrier that we often encounter in electrochemistry, because free energies are additive. But of course, what's kind of complicated is this little stoichiometry term, the N value, kind of is what turns all these kind of our intuition on its head, that the potential values that we see for hydrogen peroxide, O2 to hydrogen peroxide to water are not additive as it relates to the net 4-electron transfer. They're actually O2 to, because it's a 4-electron process, is actually the average of these values. So it sits right in the middle. So anyway, so this is just one of the principles that I had to kind of work through when I was kind of getting into electrochemistry, because I found it non-intuitive that you can't add redox potentials. Okay, so let's come back to this term dioxygenase. And so the idea is that we want to be able to transfer both oxygen atoms by splitting oxygen evenly and then transferring it to the substrate. And as I mentioned, nature doesn't have this reaction at its disposal, doesn't do it with enzymes. And so at least not in the form where we're kind of oxidizing two interesting substrates, certainly not of the type of methane or the types that I show here, because the ones that I show here, alkene to epoxide, thioether to sulfoxide, methane to methanol, you'll see that those are the potentials that tend to be highest amongst the organic oxidation reactions. It turns out standard potentials for organic oxidation reactions are really not very high. These are amongst the highest you'll see. And so especially epoxidation, because you're making this strained ring. So, but even that value is not that high, right? Because we have an oxidant that's at 1.23 volts. And so we have more than enough driving force. If you like to think in terms of free energy, we have 20 to 30 kcals per mole available to us to drive the double oxidation of 2 equivalents of propene to epoxide. And so there's an ethylene oxidation process that's run in industry. It's about the only real kind of dioxygenase that's practically implemented. And so the question is why can't we do this? Well, it comes down to kinetics, of course, that even with this amount of driving force, we still have insurmountable kinetic barriers that go into breaking the OO bond evenly, and then having enough energy left over to transfer that oxygen atom to the organic molecule. So this is kind of where Osmal Hoke in my lab was intrigued enough to kind of follow on this theme and say, we've been working on these energy reactions that I mentioned at the very beginning. We have this ORR reaction, oxygen reduction. We also have water oxidation that takes water to O2. These have the biological counterparts. These monooxygenases is a reductive activation of O2, where we now transfer an oxygen atom. Turns out in nature, there's also dehydrogenase enzymes, like these molybdopterin enzymes, like xanthine oxidase, for example, that will bind a water molecule to molybdenum to make a metal oxo, that will do substrate oxidation by oxidizing a bound water molecule through a metal oxo. So can we put these together where we have a 2-electron reduction of O2 to do one oxygen atom transfer, and then a 2-electron oxidation of water to make another oxo? If we put those together, the net sum is essentially a dioxygenase reaction, where the only cost is the energy input that you get from electrochemistry. So that's essentially what we decided to do, was to use, in this case, what we identified. I'm kind of giving you just an abbreviated version of this story, but we found a manganese porphyrin that would actually mediate a reductive activation of O2 with very efficient oxygen atom transfer, almost unity Faradaic efficiency. to do an oxygen transfer to a thioether. Separately, that same porphyrin could undergo water oxidation to make the same metal oxo to drive the thioether oxidation to sulfoxide. So both the reductive half reaction and the oxidative half reaction generate the same intermediate and drive the same product. In electrochemistry nomenclature, this is a linear paired electrolysis because you're taking the same substrate that's undergoing oxidation at the reductive side and at the oxidative side, or the anode and the cathode are both mediating the same net reaction. So thus linear paired electrolysis. So you need essentially the water molecule here is then used over here. In a formal sense, we don't worry about whether it's the same water molecule. We have ample water in the medium to carry out this reaction. But nonetheless, the idea is that our net reaction is one molecule of O2 drives a double oxygenation of the substrate. And so this is kind of acute, and I think one of our goals, of course, is how do we design now better catalysts? So this provides a template for now the design of improved catalysts for oxygen atom transfer, because we now have an energetic window that we've defined according to the potential here, and the potential here is essentially the electrochemical energy that we had to pay to carry out this transformation. And as I mentioned, this is a thermodynamically favorable reaction. So we have, 20 kcals per mole that we have available to us. We had to supplement that by another X kcals per mole, which again, I'm not going to get into all the details. But the idea is that our goal is to now use this as a template to now learn and understand how to do more efficient oxygen activation as well as oxygen atom transfer, such that we don't need that electrochemical energy input. Okay, so that's kind of a little kind of setup that kind of connects our world of aerobic oxidation to electrochemistry, because what we realized in doing this was that there's actually a better process. And in fact, through some interactions with GSK, we decided to focus on translating this to an electrochemical oxygenation process. So if you're in pharma, you don't really necessarily want to combine an O2 with an organic solvent. As I've come to learn, of course, over working with pharma and aerobic oxidations, that this still presents challenges, even though we've surmounted this challenge through flow chemistry and other like. In fact, going back to Tianning's work, she was one of the first to actually implement this in flow, the aerobic oxidation. But the idea is can we just do what we would call reagent-free oxygen atom transfer? Essentially do the oxidative coupling of water and an organic molecule to make a sulfoxide in this case, basically without requiring any stoichiometric oxidant. So that's the opportunity that electrochemistry presents, because the hydrogen or the protons that we lose upon water oxidation here to make the metal oxo, those protons can be combined with the electrons that we derive from this oxidation process, can then be recombined just to make H2. Okay, so that's the goal. Turns out that Osmol teamed up with a younger student in the lab, Tian Xiao. And I think that one of the take-home messages in this study is essentially showing how this tunable catalyst design and thinking about mediated electrochemistry really offers new opportunities for organic electrochemistry. Obviously, nowadays, mediated electrochemistry is now widespread, but I think the idea is that as you think about doing direct electrolysis or even halogen-mediated electrolysis, the idea is there's not much tunability. So if you look in the history of organic electrochemistry, there's a lot of dominated by direct electrolysis and halogen-mediated electrolysis. By being able to tune your mediator, you now expand the scope of potential, as much like the whole field of like this we just saw with Tianning, how you can tune the ligands, you can tune the catalyst in such a way as to optimize reactivity. This is the opportunity that mediated electrochemistry presents. And so that's essentially what this study showcases. I think for time's sake, I'm going to skip some of this very interesting work, kind of showing how the counter electrode actually is a very key feature that you have to account for. We were actually seeing that the substrate was actually serving as the source of electrons. It was getting reduced, it was getting reduced at the counter electrode at the cathode when we were driving the oxidation. So we were kind of shooting ourselves in the foot when we had more challenging substrates. Turns out just by adding a proton to the solution, it turns out we bypassed that, and now we could get quantitative yield just by adding acetic acid, by accounting for what's going on at the counter electrode. A little scope, I think that the message here is not the details, but rather that it shows broad scope. I think the other feature is the tunability. These are the series of different catalysts. This is a chloride-based mediator pathway. This is a direct electrolysis pathway. They actually work. They actually make some sulfoxide, but the best yield is coming by tuning the manganese-based catalyst. And in almost all cases, you find that the colors associated with manganese are going to end up at the top. And so by having access to a metal-based catalyst where you can now tune the electrode, the properties of the mediator, you can achieve optimal performance in these reactions. Darren Poole at GSK sent us a portfolio of their molecules that they found they had in their building block library with their sulfoxides. Again, we just subjected this now to this HDE chem reactor by the Merck team. Song Lin, Deepa Kalyani at Merck, and Song put this HDE chem, which is now commercially available. Basically, using that as a platform, we could set up a little screening apparatus that they've now used at GSK on occasion to essentially look at different conditions for electrochemical thioether oxidation. Again, the manganese oxo method, the black bars are almost always the highest bar across the board, and you get a reasonably good hit rate across this portfolio. Not everything works, but in many cases, you get quite good performance coming out of this assay. Unfortunately, Soa put some slides together on some new work that she's doing on epoxidation. I didn't have a chance to put that into the slide, but I just want to give a shout out to Soa, who's now adapting this to other oxygen atom transfer reactions. Osmol is now also working on N-oxygenation. But the idea is that these would be eminently scalable if the chemistry works, of course, but the idea of avoiding altogether the need for strong oxidants like MCPBA or your classic hazardous oxidants that we tend to want to avoid. Okay, I want to shift gears, and in the last portion of the talk, I want to focus on reductive chemistry. So if we can do this reagent-free oxidation, what about reductive chemistry? And this, of course, I've taken so much inspiration from my colleague Dan Weiss, who's been one of the pioneers in this space of cross-electrophile coupling, a very efficient process for bringing two coupling partners together to make carbon-carbon bonds. And so in this case, there's so many opportunities here. Tianning's highlighted some of them, even though it wasn't necessarily in the context of cross-electrophile coupling. But the idea of using nickel rather than palladium, the idea that, and this is one of kind of Dan's themes, is all these organic electrophiles have much more abundance than the corresponding organometallic coupling partners. And so that expands the scope of the substrates that you have available. So for diversity, if you're in process chemistry, it means your substrates are lower cost. And then comes the challenge, right? So you're often dealing with these metal powder based reductants. And so if you want to scale, it'd be really ideal. There's many reasons. I won't get into all the pragmatic issues associated with scaling kind of with metal powders. But then there's also the issue that you're dealing with two electrophiles. And so how do you get cross selectivity without just getting the homocoupling or the protodehalogenation byproducts? Because you're reducing, what stops you from just reducing all the way and replacing with a proton? So these are some of the issues that we've been trying to address now from this electrochemical perspective. I want to highlight first this story that Jiming has pioneered in the group, which is essentially asking the question, what is the actual reduction potential of these metals? Because you can go to these Poor-Bay diagrams. This is essentially a measure of potential as a function of aqueous pH, but this is aqueous conditions. And this is largely where we get our intuition. For example, most of us who work with this chemistry would have the intuition that manganese is a stronger reductant than zinc. Okay, that's fine. But what is the actual reduction potential? Like when you take a CV of your reaction solution, you find a nickel redox potential. Where does your where does the reductant sit as a function of potential? And it turns out we don't actually know what the reduction potentials are in organic solvent. And so that's, we're typically working in organic solvent. So what is the potential? So it turns out that there's an age-old technique. It's not a new technique, but it's one that hasn't been applied to this circumstance, which is something called open circuit potential measurement. Looks like a little typo I need to fix. But then you have metal ions in solution. So you establish a well-behaved thermodynamic system where you have a mixture of the metal ions in solution and your metal as a solid. So there's going to be some thermodynamic equilibrium between them. And it turns out that by not passing any current, you just record the potential between your metal electrode and a reference. That will actually define the so-called open circuit potential. And you can actually define the potential of zinc metal under any set of conditions that you present to it under these conditions. And so you can get manganese, you can get zinc. And so this is what we did. We basically just started measuring this. Again, the details are maybe not the crucial piece here, but the point is with different solvents shown here on the left, different additives in the corresponding solvents on the right, the details are in the paper, you can basically map out what the redox potential of your reductant is under these conditions. And I think there's a couple of just quick take-home messages. One is, notice some solvents show some remarkable deviation from what you might expect. Like there's some minor variations of the redox potentials across these amide-based solvents, and then you get into DMSO. You may see some variation of DMSO for zinc relative to the amide-based solvents or imide solvents. But then there's acetonitrile. Look what happens. Essentially, zinc and manganese pop up, and they're much less reducing in acetonitrile. This is manifested in the literature, although not acknowledged at the time. So Dan and his group had published this, for example, this cross-electrophile coupling. It's just a simple substrate. They obviously have more interesting examples in the paper, but I think it's a nice representative example for kind of development of the method. And they showed that when they use zinc as a reductant in acetonitrile, it didn't work very well. However, since we now know the redox potential of zinc in DMA, we can actually apply that potential in acetonitrile, and we find that the yield of that cross-coupling when driven electrochemically at the potential of zinc using electrochemistry now is quite good. So this is a case where it actually, and we see, here's, for example, I think Tianning showed a nice example of kind of halide effects. Halide effects are almost always, as Tianning showed, influencing, for example, the reactivity of the organic molecule with nickel. But we can't, in these reductive cross-couplings, we can't exclude the possibility, or at least we should be considering the possibility of how the halide actually alters the redox potential. Notice the dramatic change in redox potential here in acetonitrile as a function of the halide additive. And so undoubtedly, the halides are influencing the nickel-2 chemistry and the coupling chemistry, but it also affects the driving force of electrons going into the system. I mean, this is a span of like nearly 600 millivolts, 500 millivolts across this window. You can even see that here's in one case where zinc actually pops on the other side of manganese. And so, I think our intuition, can go awry sometimes if we don't take into account the conditions under which we're operating these reactions. It's a nice opportunity, I think, for those of us who do nickel redox chemistry, whether it's chemical or electrochemical. We often will take a CV of our reaction medium. And what you can do is you can actually see where the redox potentials are for the nickel. And you can correlate now, because you know the redox potentials of zinc and manganese under those potentials, you can now start to correlate how those potentials impact kind of the chemistry that might be happening. Okay, I won't go into details partly for time, but essentially this is a nice way of calibrating kind of the redox potential of your metal. It's a very simple technique. It can be readily adapted to any conditions. So I'm sure that the conditions that we show here are not necessarily the conditions you might want to use. And so it's easy to go measure it yourself if you have a potentiostat. Finally, I just want to kind of highlight from this study, I want to highlight, now that we know we can run reactions with zinc, we can run them with manganese, and now that we can measure the zinc potential and the manganese potential, we can compare how does zinc compare to the redox potential of zinc, but doing it electrochemically without zinc as the actual source of electrons, but rather using the cathode as a source of redox power, but at the zinc potential or at the manganese potential. And of course, the beauty of electrochemistry, and part of the motive kind of underneath this was to say, look, we don't want to be fixed to manganese and zinc. We want to be able to have an infinitely variable redox potential. And so we did this in the context of this kind of cross electrophile coupling using these Katritsky salts. These are some representative data. Essentially, what you do if you kind of squint and don't focus on too much detail, what you see is that blue and blue, basically you see the blue bars and the red bars largely correlate within themselves. So what we're doing is reducing with zinc or reducing electrochemically at the zinc potential, reducing with manganese or reducing at the manganese potential using electrochemistry. And there's a rough correlation. Now, obviously there's issues like mass transport, there's surface characteristics of the metal versus the electrode that could kind of lead to these variations that we see. But the other point that I want to highlight is, so not only is electrochemistry, to a first approximation, doing a good job of replicating what you get out of the metal at their appropriate redox potentials. The point is that the optimal potential is often not at the zinc potential or manganese. It's almost always something else. Sometimes it's less reducing than zinc. Sometimes it's more reducing than manganese. Often it's in the middle somewhere. So the ability to tune your potential, if you're a process chemist, is how you optimize the reaction, and that these reactions and the intermediates that are involved in these complicated catalytic cycles, the potential at which you deliver those electrons can have a profound influence on the outcome of the reaction. And so this is a knob that we often don't use when we're just using a chemical reductant, which has a fixed potential. Obviously condition variations can be made, but the idea is that electrochemistry gives you that infinite tunability that you can really exploit to optimize your chemistry. Okay, a couple other short stories before I close. We have this very interesting project with BMS that's just coming to a close. They have this reaction. They had a very nice study. I should have put the citation in here. There's a JOC paper with Greg Buettner as the lead author here, basically looking to make this bond. And the optimized conditions turned out to be this two-step Suzuki reaction followed by hydrogenation, so taking advantage of established Suzuki coupling. So that's 2 palladium steps with a costly building block. And the question is, why can't we do this just directly from 2 inexpensive building blocks through cross-electrophile coupling? It was one of the methods that they tested in their conditions. And the challenge, and this was kind of the question, is can we do this? It was, as I mentioned, one of the methods they tested. The downside is that we often see byproducts. Okay, and so this is kind of the challenge of cross-electrophile coupling, is that you can make the bond, but you often see the homocoupling product or the protodehalogenation product. That's evident here when we run this electrochemistry. This is in an undivided cell using zinc. It turns out that this basically replicates, because we're using a zinc, we're putting zinc ions into solution, so we have a zinc electrode. We get the same basic pattern as you get with zinc powder. Okay, and so what Luana tried, and I still can't remember why we tried this, but she tried using a divided cell, and all of a sudden, all the byproducts went away. It was almost a perfectly selective reaction. And now, by using a divided cell, there were no byproducts. It turns out that this is held again. It turns out that whether it's zinc, whether it's iron, it turns out that the byproducts you make actually change. It turns out iron actually favors the biaryl. Zinc favors the protodemetallation. Maybe for discussion, we can discuss why that might be. Then you've got magnesium that's actually causing problems. We're not getting full conversion. But the main message here is that the origin of these byproducts is actually attributed to the metal ions that you're using in the reaction, that are being generated from the sacrificial anode. And so it turns out that this is actually replicated in the context of flow chemistry. And so even if we go to scale up in a parallel plate reactor, we get similarly perfect selectivity where we don't see these byproducts being formed. And I think this is kind of a fun little kind of notion that using electrochemistry, you actually can do a divided cell. Now, I would argue that most people doing electrochemistry say of what we really want is an undivided cell. But if you think about the counterpart, if you're going to use metal ions as powders or metal powder reductants, you don't have this option at your disposal. There's no way to segregate the source of electrons from the catalytic reaction. And electrochemistry gives you that access. And that's essentially what this flow chemistry is basically showing, is that you now have a mechanism to actually segregate the source of electrons from the chemistry that's actually happening in the cathode compartment. And so that's a kind of a unique kind of learnings that's just coming out of this recent study with BMS. And so let me close, because I titled this talk kind of nearly reagent-free electrochemistry. So if you're going to do reduction, what is the best source of electrons? Now we might want to use water electrolysis, because that's what's done to make solar fuels and hydrogen, for example. The problem is nickel chemistry doesn't always play well with water, and it starts to change the behavior. It's not always so susceptible to water, so it can tolerate some. But it turns out that you would actually transport a lot of water into the nickel reaction compartment if you actually try to run an electrolysis by doing proton or hydrogen oxidation on the anode. So what we decided to do, and if again, this kind of just comes back to basic organic chemistry principles, hydrogen oxidation is actually not a difficult problem in organic chemistry. Organic chemistry, we call it hydrogenation, right? We're reducing an organic molecule, but by the corollary is that we're oxidizing hydrogen. So if we could hydrogenate a redox active organic molecule, we have the ability to set up a flow cell where we're now oxidizing something that works well at the anode. Turns out it's very difficult under non-aqueous conditions to oxidize hydrogen directly at the anode. But it turns out hydroquinones can be readily oxidized. So this basically, by setting up a flow cell, we can now drive nickel cross electrophile coupling with hydrogen. And in reality, we actually need electrochemistry because hydrogen chemically is not a sufficiently strong reductant to actually drive the reduction of nickel to the potentials that are needed. This is the standard potential of hydrogen in the medium that we're operating, and it's not a strong enough reductant for these nickel redox intermediates. So we're going to need to have a power supply to supercharge those electrons coming from hydrogen. It is, of course, capable of hydrogenating anthraquinone. This is the basis for the anthraquinone process that makes hydrogen peroxide. So you can essentially hydrogenate this quinone. So we can do that, and then in turn use that as the source of electrons to drive this chemistry. That's basically shown here, where we're going to do anodic oxidation of a hydroquinone to quinone. In solution, in this case in a slurry, we're going to essentially hydrogenate the quinone to the hydroquinone. So basically in solution, we're doing the hydrogenation. At the electrode, we're doing the oxidation. So we're just kind of setting up a cycle, consuming hydrogen, but using those electrons now to drive the nickel chemistry over in the other compartment. And so now we can carry out this reaction to make carbon-carbon bonds by doing the reduction of the corresponding nickel co-catalyst. This is just essentially what this looks like in a little bit less schematic. It's a little bit more detailed, still schematic, but kind of illustrating what we do. We essentially create a reservoir that has our flow solution where we have a packed bed reactor in which we co-feed hydrogen and the solution coming from the reservoir to do the hydrogenation of a quinone. That feeds into this reservoir. The reason we use a reservoir is so that we can decouple the flow rates on this side and this side. So we can optimize the flow rate here and the flow rate here. You get a standard state of charge because you're oxidizing the hydroquinone here, you're reducing the quinone to make hydroquinone here. They mix in here, and so you get a steady state of charge. You can actually show this. You can turn on the hydrogen-only loop. So when you just hydrogenate, you just build up the hydroquinone. If you just turn on the electrolysis loop, you build up, this is UV vis, you basically just build up the anthraquinone. And if you turn them on both, you build up this steady state of charge that basically has this mixture that's predominantly anthraquinone. And of course, you can adjust that state of charge basically according to the rate at which you drive this side versus the rate at which you drive this side. Then what we can show is that we can achieve current densities kind of right now from 0 to 16, at least in the original study. We're now higher than that. But it turns out we don't need 16 because Tianning made this point. Turns out that nickel catalysts are often very slow. You actually only need a current density of about 4 milliamps per centimeter squared. So that basically is where you get your best selectivity. These are the byproducts that we've talked about previously. Just get a little bit of the biaryl coupling, in this case, a BIP type derivative. And we get quite good yield in this case of this coupling. And so this just shows the reactor bay that the Merck team shown here. Some of you may know Dan and Francois and Cecilia. So what you see is the reactor bay, and you can see the different components. You can see the hydrogenation packed bed reactor. You see the pumps. You see the reservoirs that we're using kind of here and here. Additional pumps, and then you can kind of see this kind of parallel plate reactor. It turned out that we use a stack of 4 parallel plate reactors for the scale up in this chemistry, and that kind of just gives you a little bit of a sense of the scale of the process that we use to make these kind of pharma level intermediates that we found from the literature largely to demonstrate in this type of flow process. So anyway, with that, I think I'm going to close and just highlight essentially again that oxidations, they actually can be done reagent-free. And I think one of the strategic opportunities replacing these kind of undesirable oxidants to do oxygen transfer, and then down in reductions, there's a lot that can be done essentially thinking about how to drive kind of reductive chemistry, but I think we can go green on this side too by using hydrogen or other kind of sustainable sources of electrons. And so that's the focus of ongoing study. So it remains for me to thank the team. So we have an oxygen transfer team. So just a shout out to Osmal Hoke and Tian Xiao, who did a lot of that work. also the GSK team that played along and delivered numerous substrates along the way. And then a cohort of people from the Jiming kind of leading a number of the studies, Luana leading the BMS collaborations, Matt and Jack leading the Merck collaboration. And then there's a number of partners. Dan Wykes has been a wonderful collaborator all the way along, as well as kind of our partners in industry. So with that, I'll thank you and conclude the presentation.
All right, yeah, that was fantastic. A lot of math from me, but that's okay. That was really neat. I really like the types of reactions that we can do with electrochemistry and the oxidations with, without the molecular oxidants is just really, I think that's fantastic. Just curious, that wonderful chart you showed about the changing the potentials with the different additives and the different solvents. I mean, that alone is just really amazing work, but also really helpful in terms of deciding, where do you use different solvents and things like that based on your substrates for solubility reasons, or what drives the difference in that makes the, like, chloride addition being so much more highly oxidizing than like the iodide.
I mean, I
27,
think
I think, yeah.
this is all essentially a thermodynamic question, right? So what you're basically asking is, what makes nickel 2 salts more stable? What makes them less stable? Because the metal's not going to change a lot. At least our premise is that the thermodynamics of the metal are not going to be dramatically affected by what's out in solution. But the nickel 2 salt is going to have dramatic changes. I think that's what's driving, for example, can you see my cursor?
Yep.
So what's driving the acetonitrile numbers is that when you have a non-coordinating anion, you basically have solvated acetonitrile solvated nickel or zinc. And that's what's basically making it so unstable, because acetonitrile is an electron deficient ligand. And so it makes it what shall we say? It's easier to pump electrons in. By the time you get to chloride, you've now stabilized the zinc. And so now it's harder to get the electrons in to make zinc metal. And so essentially that's how you're thinking about what's the relative stability of the oxidized and the reduced state. If the reduced state is essentially steady, you're basically asking what's the stability of the salt, the zinc 2 salt. And that's what's causing the swings.
That's really neat. Yeah, if anybody else has questions, please put them in the Q&A. We're right at time, but you're free to stay a little bit longer. I don't see any more. Steve, anything from you guys? That was some really interesting collaboration work there with your colleagues at Merck. All right, well, I think we're not seeing anything come up in the Q&A. Excuse me. And let me check the YouTube as well. Got a bunch of people over there, but only a whole bunch of thumbs up. So, all right, Shannon, thank you so much. And Shannon and Tianning, just wonderful to have both of you folks here. Great couple of pairs of talks. And thank you to all the attendees for being here. We had quite a number. I know Steve had a bunch of folks at Merck all together in a big room. So had a lot of folks. Any final comments, Steve?
No, that's everything for me. Thanks to both of you. Really appreciate it. This is really great talks.
Okay. Well, thank you again.
Great job, folks.
Yeah.
Thanks. And Alan, you can shut it down and we'll just keep talking. Okay, perfect. All right. Again, thank you both. That was wonderful. Tianning, it was so wonderful to finally meet you, talk in person, and hear your work. And Shannon, always a pleasure. That was fantastic. Some really neat things. You get making when you're using MCPBA and stuff with sulfur, sometimes you get a lot of sulfone. Do you see that with when you're doing it with electrochem?
In the batch scale, we were not seeing any sulfone. It was like,
wow, that's really cool.
Complete break. We started trying to scale it, and then we started seeing some sulfone. And I think the issue is that as you go to higher electrode potentials, because you get more cell resistance, I don't know how much you think about electrochemistry, but you get more cell resistance, your electrode potentials have to swing higher to maintain the rates, and you start to see kind of a background overoxidation. So So you do see some, but we haven't optimized it. But I think you would get very good selectivity. But there's a nice Merck paper actually about making sulfones that I really like, the chloride mediated. So there's a team at Merck that put out a really nice. And I would argue that at least in most spaces, the sulfone is probably kind of the more common target for these superoxidations.
Yeah, I was one of the things I was thinking about is over the years I've seen where you have a thioether or some sulfur in your molecule somewhere, and the metabolite folks are always asking for, can I have the chiral sulfoxides? Because they want to do testing on it because they'll see it as an impurity or a metabolite. Can you ligand your way around a chiral sulfoxide?
We're working on it.
I figured.
I mean, to be honest, I'm not sure how important it is. And so, I mean, it's a matter of allocation of resources. But certainly asymmetric oxotransfer is on our radar and something we're beginning to explore.
Cool. No, I won't ask any further. No, that's really neat. So very cool.
Yeah.
Oh man. All right. Well, I skipped lunch for this, so I'm gonna run off and go get myself some lunch.
Okay.
So I will
All right. Well, thanks
thank you all again. Alan, we got to talk. They want to do the Ewok one in early December, so we might have to do another one of these. Okay. So we'll chat about that. Folks, again, Steve, it's good to see you and have a great day.
Good to see you,
Bye,
Tianning.
everybody.
Bye.
Good to see you, Shannon.